Hello everyone, and I'm back with another video, and today we'll be discussing linked list cycle 2. So this question is a continuation of linked list cycle, the previous video that I did on this channel. And if you haven't seen that video, definitely go check it out because we're going to be using the concepts that we discussed in that video, like Floyd's algorithm here too. So yeah. Now this question says that given the head of a linked list, return the node where the cycle begins. So by this what they mean is that return the node where you first enter the cycle. So in this example it would be 2. If there is no cycle, then return a null value. And an important point that they mention is that you shouldn't modify the linked list in any manner. So yeah, so this question again can be done using hash maps. Uh, but that would again result in a solution of uh, linear space complexity, and I would like to suggest an approach here that just works in constant space complexity. So the approach that I'm going to suggest is just going to be an extension to Floyd's algorithm. Uh, yeah, so Floyd's algorithm was discussed in my previous video. I'll put the link here if you need a refresher or if you haven't seen that video yet. Uh, but what I'm going to do now is I'm going to explain what this extension to Floyd's algorithm is that will help us in identifying this node where the cycle begins. Uh, and after that, I'm going to code it up, and in the end, I'm going to explain why this approach always works, right? So so let's just see what the approach is first. So this is a linked list that I have here. N is the number of nodes in this cycle, and L is the number of nodes that come before the cycle. So what's going to happen now is that I'm just going to execute plain old Floyd's algorithm, right? That's my first step. So in that case, what will happen is S moves once, the fast pointer moves twice, the slow pointer moves once, the fast pointer moves twice, the slow pointer moves once, fast pointer moves twice, the slow pointer moves once, fast pointer moves twice, the slow pointer moves once, the fast pointer moves two times, the slow pointer moves once, and the fast pointer moves twice, the slow pointer moves once, fast pointer moves twice, slow pointer moves once, and the fast pointer moves twice, and they end up on the same node, right? So yeah, so this is going to be my first step, just executing Floyd's algorithm. Once I've done this, what I'm going to do is I'm going to shift the slow pointer back. So once I've done this, if I don't detect a cycle in the linked list, I can just return a null value because there's no cycle in the linked list. But if I do detect a cycle in the linked list, then I'm going to move my slow pointer back to the start of the linked list. I'm also, and from now on, my slow pointer and fast pointer will move one node each in every iteration. So my fast pointer was moving two nodes first before this, but now it's just going to move one node only. So I'm just going to start moving these one node at a time in every iteration. So in the first iteration, the slow pointer moves one node, the fast pointer moves one node. In the next iteration, the slow pointer moves one node, the fast pointer moves one node. In the next iteration, the slow pointer moves one node, the fast pointer moves one node. In the next iteration, the slow pointer moves, one node, the fast pointer moves one node, and in the final iteration the slow pointer moves one node and the fast pointer moves one node. And what we see here is that both of them coincide again, and this is where I want to stop. When they coincide again, they will always coincide on the node where the cycle starts. So all I need to do is return this node now. And that's basically the algorithm to solving this problem. So let's just code it up now. Coding it up is pretty easy. So all I need to do is implement plain old Flyod's algorithm first. So I'm going to say s is equal to head, f is equal to head, and count is equal to 0, while f is not equal to none. If s is equal to f, then count plus is equal to 1. And I've already discussed this in my previous video, so if you guys are a little lost as to what I'm doing here, you should just go and check that out. Wait, I just think this is a little bit, okay, yeah, it's fine now. So if count is equal to 2, then break. So here in my originally we were just returning false, right? Because we didn't originally we were just returning true because we detected uh, a cycle in the linked list, but here I'm just going to break it for now and deal with it later. And if it isn't true, then I just want to do s is equal to f dot next, f is equal to f dot next, and if f is not equal to none, then f is equal to f dot next, right? Yeah, so once this loop breaks somehow, I'm just going to check if count is not equal to 2. If count isn't equal to 2, that means that we didn't find any cycle in the linked list. So I just have to return a null value here. So I'll just return none. And otherwise, what I have to do is I have to shift the slow pointer back to the head, right? And then I need to keep uh, and then I need to use a loop in which I increment my slow pointer and fast pointer each by one step every time. So while s is not equal to f, s is equal to s dot next, and f is equal to f dot next, and that's all, right? Yeah. In the end, when this loop terminates, the node that both of these pointers are pointing to will just be the node that represents the start of the cycle in the linked list. So I can just return any of them, return s or return f, anything works. Let's just run this once to see if it works or not. Yeah, surely it works. And let's just submit it. Great. So this solution works, and it works in linear time with constant space usage. So that's all well and good, but how does it actually work? Like, why does this algorithm end up in both these pointers coinciding at the node that I need to return, right? So to see this, let's just work through Flyod's algorithm in a little bit of a mathematical perspective. So I'm going to use modular arithmetic here, and if you guys are uncomfortable with that, be sure to like learn about it a little. Uh, yeah. So what's going to happen is that when I'm using Flyod's algorithm, so let's consider this stage in the Flyod's algorithm, right? When S has reached uh, this node in the Flyod's algorithm, we haven't moved out of the Flyod's algorithm yet. If S is at this node, then that means this F would have traveled double the distance of S, right? So it would have traveled 1, 2, 3, 4, 5. This is how much S traveled, and then it would have traveled 5 again, because the fast pointer travels 2 times for each time that S travels. So it would have traveled 1, 2, 3, 4, 5, right? So when the slow pointer is just at the node that is the start of the cycle, the fast pointer is at this node that is labeled 1, right? In a general situation, this fast pointer is going to be at a node uh, that is given by L mod n. Okay, if I number the nodes like this, 0, 1, 2, 3, where 0 represents the node that is the start of the cycle that is the start of the cycle, then this fast pointer is going to be at L mod n index node. And the reason for this is that the slow pointer has moved L steps, right, to reach here. The fast pointer has moved 2L steps from this point. So the first L steps it just reaches here, and the next L steps it takes inside this cycle. So if the number of nodes in this cycle is n, the index of where it ends up will be given by L mod n, by modular arithmetic, right? Now, okay, so this index 1 is going to be L mod n, actually, right? Now what I want to find out is how much this fast, so basically what I'm going to try to find out is how many iterations will it take for this fast pointer to catch up to this slow pointer, right? So an important point to note here is that in every iteration, the fast pointer reaches uh, one node closer to the slow pointer because they're inside a cycle here. So inside this cycle, the fast pointer is going to move 2 times, right? So if you see here, the distance between the fast and the slow pointer is basically how much the fast pointer has to move to reach the slow pointer. So it's this distance, not this distance. So the distance between them right now is 1, 2, 3, 3 nodes, right? But if I use one iteration of Flyod's algorithm, the fast pointer is going to move 2 steps within this cycle, and the slow pointer is only going to move 1 step, right? So the fast pointer is now 1 node closer to the slow pointer than it was before, because now it just has to move, it just has to cover 1 or 2 nodes to reach the the slow pointer, right? So what my question is that when this slow pointer enters into the cycle for the first time, so in that stage of the Flyod's algorithm, how far is this fast pointer from the slow pointer? How many iterations will it take for the fast pointer to reach the slow pointer? So that'll just be the number of nodes that it's far from the slow pointer, right? So that'll just be 3 iterations, because in every iteration it'll become 1 node closer to the slow pointer and it's 3 nodes far away from the slow pointer. So in 3 iterations it'll be right where the slow pointer is, right? Even if the slow pointer moves, because the relative velocity between them is like 1 for the fast pointer. Yeah, so we figured out that uh, it'll take 3 iterations for the fast and the slow pointer to come at the same node again, and for the Flyod algorithm to basically end, right? So in 3 iterations, where will the slow pointer end up? So that's pretty simple, right? It'll just end up at 1, 2, 3 here, right? And because we already figured out that the fast pointer is going to catch up to the slow pointer, we'll know that it's going to, just be here too. So yeah, so both of these are going to end up at this node 3, right? And this 3 was actually the number of iterations that I had to run the Flyod algorithm for after the slow pointer had reached uh, the start of the cycle, right? So what the 3 basically is in terms of L and N would be how far the fast pointer is from the slow pointer, right? If I take it like this. So that's just going to be 0 minus this thing, the index of the fast pointer, right? But this is going to be in like this modular integer system. So that's going to be 0 minus L mod n. Okay. So for example, in this situation, L is 5 and N is 4, right? So it's going to be minus 5 mod 4, which is just minus 5 mod 4 is like 3, right? If you, by modular arithmetic rules, it's 3. So yeah, so this expression basically will give us the index of the node where both of these pointers will end up at once the Flyod's algorithm is completed. Okay, so that'll be this index 3, right? And once they've reached here, okay, at this index 3. What I'm doing is I'm moving the slope pointer back to the start of the linked list, right? But before I do that, I just want you to recognize how far away this fast pointer or any of these pointers are from this, the node that we need to return. How far are they from this node? So they're just one node far away, right? If they just move one step, they'll reach this. And what is that one? So that one is basically doing this same thing again, right? Finding the distance of this node 3, finding the distance of this node 3 uh, from my 0 node in this modular system. So that's just going to be 0 minus 0 minus L mod n, right? And what is this? I'm sorry, I forgot a bracket here, right? And what does this evaluate to? So this evaluates to simply L mod n, right? Because yeah, I'm sure you can see that it just evaluates to L mod n. So L mod n is 5 mod 4 here, which is 1, right? And so that's clear that it works because they're just one node away from the 0 thing, right? So all I need to do now is figure out a way to make any of these pointers move one node in this modular system. If I am able to make them move this L mod n nodes ahead, then I'll know that I'm definitely at the start of the cycle, right? Because we've just shown mathematically that they're at a distance of L mod n from the start. So if I make them move that distance, they'll just end up at the start of the cycle. So how do I do that? Uh, so the way to do that is pretty neat actually. What we're going to use is we're going to use the fact that L is actually the number of nodes not in this cycle, right? That's what we started off with. So I'm going to move my slow pointer here to the start, and my fast pointer is just going to remain here. And now each of them is going to move one step in every iteration, right? What's basically going to happen is that if I can write L as something like, so if I can write L as something like some quotient Q times N plus uh, the remainder, which is basically L mod N, right? So this means that when we take L steps, right? So the slow pointer is just going to take L steps now to reach 0, right? But when it takes this L steps, the fast pointer is also going to take L steps, right? So it's going to take 1, 2, 3, 4, 5 steps. And the reason it lands up to 0 again is because in this modular system, all we're concerned is with this remainder, right? This quotient part is just the amount of times it's going to travel the whole cycle once and end up back on 3. This remainder part is the amount of distance it actually gets away from 3, and that in this case is 1. So if we just make both of them travel L nodes, right? Uh, then they're just going to end up on this 0th node, right? Because f will have moved L mod n times from its initial position, not considering the times it's just run the whole cycle and come back to 3. And S would have moved these L nodes and come to this start. And in the same time, F would have moved the amount that it has to move, L mod n, which is also mentioned here, L mod n, and reach the start. So both of them would collide, and the place that they would be colliding at would actually be the start of the cycle. So yeah, so that's why this algorithm works, and I thought it was a pretty neat algorithm, especially the extension that it has to Floyd's algorithm. I hope that my explanation was a bit helpful. If you're a little confused about the modular arithmetic parts or how I did these calculations, feel free to leave me a doubt in the comments, or you can go and search about modular arithmetic and read about it, because that's also a pretty important concept in computer science. So yeah, that's all for this video. I hope you liked it and I hope you learned something. uh, that's all. Thank you for watching. Bye bye.